Hello, my name is Emmanuel Balogun, and the title of my talk is Fluorine-Free Hydrocarbon PEM Fuel Cells Generating Greater than 1 watt per centimeter squared peak power density. Currently, the state-of-the-art ionomer is being used as membrane and catalyst layer ionomer for PEM fuel cells are perfluorinated sulfuric acid ionomers such as the Nafion. This Nafion-based ionomer has a lot of very interesting properties, such as its very high resistance to chemical attack and high stability, its ability to absorb large quantity of water as a result of the sulfuric acid end group which it has. It's also a good proton conductor, and it's also soluble in low boiling point alcohols, making them very good candidates to be used for making catalyst inks. However, these naphthalene ionomers entail very hazardous and complex fluorine-based synthesis. It is also very expensive and actually very sensitive to temperature and humidity, limiting the maximum temperature in which it can be used. Based on the aforementioned technical difficulties, hydrocarbon-based ionomers have actually been introduced. These hydrocarbons are non-fluorinated hydrocarbon polymers. They are cheaper as they contain monomers that are readily available in every basic chemistry lab. They can be easily fine-tuned and easily recycled. The challenge with these hydrocarbon-based ionomers is that they have very low ionic conductivities, making them not competitive with Nafion in terms of performance. Also, they are more susceptible to oxidative degradation, and they are not very durable in terms of durability, and most of them are only soluble in high boiling point organic solvents such as DMSO, and making them not very good candidates to be used for catalyst ink designs. In our lab, we've been able to synthesize a new breed of sulfonated phenylated polyphenyl multi-blockopolymers, simply called SPPBH. This new breed of hydrocarbon ionomer is able to combine both the excellent properties of the traditional fluorine-based Nafion ionomer and the excellent environmental properties and recyclability of the hydrocarbon ionomers. The SPPBH has been shown to exhibit competitive performance with Nafion. It is soluble in low boiling point alcohols, making it a very good candidate to be used in designing catalyst inks, and is also resilient to free radical attack compared to previous hydrocarbon ionomers, hence enhancing its durability. In 2017, we reported this SPPBH based MEA, and we compared its performance. As you can see in the polarization curve on the left, it actually outperforms the 50 micron Nafion N212, and in terms of durability, it was observed to be more durable than the Nafion N211. But the challenge with these results was that only the membrane used in this study was hydrocarbon SPPBH based. The ionomer within the catalyst ink was based on Nafion. So going forward, which formed the basis of my work, I'm looking at a way of optimizing a fully hydrocarbon-based MEA using the SPPBH membrane and SPPBH ionomer as binder within the catalyst layer. To determine the optimal ionomer content in the catalyst layer, there's the bottleneck problem of ionomer content. You want enough ionomer to enhance proton conductivity, but too large ionomer content would also block the pore spaces where gases need to transport, which might end up causing mass transport problem when operating your cell. So to determine the optimal ionomer content, we look at the Nafion benchmark, which was 38%, other hydrocarbon benchmark that had been reported by Strong in 2015, which was 28%, and we went lower to 10. We also checked 15% and 25% for completeness. As can be seen in our results, the polarization curve and power curve on the left actually shows that the peak power density is obtained when using 15% ionomer content within the catalyst layer. And at ionomer content greater than 15%, the power density is observed to drop. The peak power density is observed to drop, and at ionomer content less than 15 waste percent within the catalyst layer, the peak power density is also observed to drop. Previous reports had shown that Previous report by Strong in 2015 showed that at 0.6 volts, 900 milliamps was recorded, and Kim in 2019 recorded 240 milliamps at 0.6 volts. However, the full SPPBH based ionomer membrane was able to record 1.2 amp per centimeter square at 0.6 volts. This actually outperforms every other report that is in literature for hydrocarbon-based MEA. To further characterize our cell, we did an electrochemical impedance spectroscopy. The nitrous plot on the left-hand side actually was done under hydrogen anode and nitrogen cathode to determine the protonic resistance within the catalyst layer. And on the right-hand side, the nitrous plot done under hydrogen and oxygen operation shows the charge transfer resistance of our MEA. It is observed that as the ionomer content increases, the protonic resistance reduces. The reverse was the case for the charge transfer resistance. As the ionomer content reduces, the charge transfer resistance increases. So the bottleneck problem earlier was how to optimize the ionomer content such that the protonic resistance and the charge transfer resistance are optimized. And this is actually achieved at 15 weight percent, unlike previous reports that reported 20 weight percent for hydrocarbon and 30 weight percent for naphthalene-based PFSA. For SPPBH-based hydrocarbon MEA, 15 weight percent is observed to be the optimal ionomer content. Lastly, we compared a fully hydrocarbon-based system to the state-of-the-art PFSA-based system. And we noticed that the peak power density of the SPPBH MEA outperforms the naphthalene-based MEA slightly. This is quite interesting because this is the first time we would be having an hydrocarbon system that is able to outperform that of the traditional PFSA system. Although at the ohmic and activation region, as can be seen by the green and orange cycle, the PFSA naphthalene-based system is seen to significantly perform better than the hydrocarbon system, meaning that when you need to operate your cell at low current density, the naphthalene-based system is actually good. But as you're going to the higher current density, which is needed by most devices, the hydrocarbon system is seen to outperform that of the naphthalene system, showing that as a result of the lower ionic content, ionomer content within the catalyst layer, the mass transport resistance was reduced significantly, hence enhancing the performance of the fully hydrocarbon-based system. In conclusion, we've been able to show that the cell performance actually depends significantly on the ionomer content. Peak performance is observed at 15 weight percent. This is the first time we're describing a fully hydrocarbon-based hydrocarbon-based MEA with power above 1 watt per centimeter square. We also show for the first time an SPPBH naphthalene system that performs better than the state-of-the-art naphthalene system under here. Thank you for your time. I'll take questions.